So, a company called NVIDIA, I'm sorry if I mispronounced that, has come up with an exciting new way to use AI to transfer video calls. But I want to talk about how I think this technology could not only do that, but could also remarkably improve encryption and data security. So first let's go over normally how we make your data on the web secure or encrypted. And that is through a process where we take your data, and one way is we do something called differential privacy, where we throw away data we don't need, so we don't give out data that could be used in some way to harm you. You can see this in medical data where they might run a trial with participants, but they throw away their names when they report the results in a journal, or they throw away exact things to identify people. Or when you give out your banking info, you don't give out all your banking info, just what they need, so people can't use too much of it. Another method in differential privacy is you take the average of a bunch of things or some other statistical measure, and that kind of clouds up your data so you don't appear as much. Like if I want to, your income might be some very personal data, but fine, or where you're from. But I could look at a group of people in the whole college, if that's, I want to look at the average if I want to look at income data between colleges, I just take the average of everyone in that college. Therefore, I can't specifically identify any one person's income or data because I have this large averages, or other ways just kind of taking the data and putting it all together. Another way in this differential privacy technique is I add noise, so it doesn't give me exactly away who it is, but it gives you an idea, like, or I round or approximate something to throw away some data. So if I begin with income, I might just round up your income or round your income. So I don't know exactly how much money you own, but I know thing, or I could put people in income brackets. I could do it with height, I could do it with anything, put them in brackets or round. I could also add a little numbers that are fake, but they don't mess up the data too much, that you can still get useful parameters. Okay, that's one way. The other one is more encryption. In encryption, we somehow put your data or something into a program that either somehow puts a function that either mixes up, like maybe it switches, if it's text, it might switch all of A with B. Or it could be some super fancy function that it switches A and B unless A is followed by C or D, or there could be something fancier where I do a mathematical function that switches up a bunch of numbers or changes numbers like times by 10 or 20. But the thing is, it's really hard to go one way or another way. The problem with both methods, with differential privacy, the data is still there to some extent. So if you wait long enough, you can always get the data. It's not perfect. If I'm taking the averages of groups of people, if I keep taking averages of different groups of people, maybe I can figure out your number because it just eventually figure out, oh, you're contributing the most, or something like that. Work my way through it, or if I put your location off by 1 mile, every time I enter your location randomly off by a mile, eventually I'm going to pinpoint where it is by just taking the average. So eventually I can figure out, just watching you long enough, who you are, or I could look at big data sets and try to guess who you are. Even though I didn't have your name, I have your height, what hospital you visited, when you visited, stuff like that, and I slowly could try to piece the pieces together. The problem with encryption is there's always a pattern, and the pattern I can figure out. One famous way of deciphering things is that the simplest way of deciphering things, the simplest way of encryption is if I switch two letters, let's say A and B. If I know how much A is supposed to appear in a sentence on average and B is, I can figure out, hey, those ones are that. That's called frequency way of deciphering. I look at the letters and how much they're supposed to appear and how much the letters appear in my encryption. Then I try to guess what the letters are, and I keep doing those guesses until I figure it out. So none of these methods are perfect, and we found much more complicated ways of doing them work much better, and oftentimes we combine them. So that's the basic idea there. Now, NVIDIA first came up with something that's going to seem totally different, abstract, and has its own wonderful uses. I think it could be used for not only for videos, like they say, but for just any type of data streaming back and forth to reduce bandwidth. And that is they used an AI, which I'm going to show you, and how remarkable it is to recompress the data. So normal compression uses this many bytes of frame for this picture, 97.28 kilobyte frame. They only used 0.1165. That's over 100 times improvement, nearly 1,000 times improvement in how much less data they used. Nearly 10,000 times improvement. Wow, just orders of magnitude. And the way they did that was AI was better able to predict, and they show with this picture, better able to predict exactly what you need in a picture. So they just look at the key points and just how it changes, so you don't have to send out all the data. And it recognizes, and why AI can do this better than human beings, because it can recognize particularly what's important. Particularly what's important, like these little dots. It's kind of hard to see it, so I'm gonna try magnifying it a little better. Yeah, it's not really showing it very well, but it only like key dots like the eyes and stuff, and it shows how those key dots move, so you can extrapolate everything else, and it makes key points to give you a better idea of people's faces. Now, this means a lot less data is transmitted. Great. But how do they do this? Well, this is how they do it. They use something called a GANs, which is a Generative Adverse Neural Network. There are many versions, and they don't tell exactly how it works. And an AI, and what it does is, first we have, and this is a whole thing about the paper, and I'll put these links down. First, there's a generator that sends data and a picture, and this has a fake data. Then it has a discriminator that looks at the data and tries to tell if it's real or fake data. If it tells it's real data, this discriminator trains on real data and fake data. It gets better and better at telling the discriminator over time, gets better and better at telling real data, real pictures sent from the generator, the fake picture it sends. But then when the generator then looks at how this detects the real data, and looks at how it figures out from the fake data, and it gets better. Now in the generator, you put random noise. Now the random noise is what is used to make the picture. It gives a starting point. So it takes this noisy thing, and have you ever looked like a random dots on a screen or TV, or maybe something in the sky and see like a face or something? Like that's kind of what it does. It looks at random noises and kind of uses to start modifying it until it gets a face or something real. However, the idea with the paper is, what if we could instead take this data and do it in reverse, where we take a real picture and see how little data we can get out of it. So we run it in reverse and get an axle, just the random noise. Then we put this random noise into this generator again, and then that generator produces a picture. So this random noise, so instead it's now not random noise, it's an actual picture. So we put a picture through it, get this random noise, and then we put that random noise back through the same thing and get a picture. They don't exactly tell you how they do this. So yeah, but this random noise can be a lot less because you can start off with a little amount of noise and spread out to final details, which is oftentimes a procedure done in gains. Because starting off with too much data, you have trouble getting the big details and focusing on small details. So oftentimes you want to start on the small details. The big deals and get to the small deals later on. So you start off with a little bit of noise, then just make the picture bigger and bigger. So how does this could help compression in the future? Well, this noise, this data stream is so small, 1,000 times small, 1,000 to 10,000 times smaller than traditional compression, that you really get rid of non-important information, which means that there's less information a hacker could steal. The first thing, it also means that you get rid of a lot of patterns or clues in the data stream because you're throwing away all this extra data you could get inferences from. You also can add a lot more fake data and fake noise to the stream to make it take up the same space. Like you can add now 10,000 times the noise and fake data to make it take a lot longer to deconstruct it. And now when you mix up the data, it can mix in patterns and stuff like that in more complex ways because you only have the core of the language, not the clues. And these cores are a lot harder to detect. But what's even more exciting is, remember I said that it trains with random noise? Part of the training has to do with randomness. Random noise is that when it's encoding, it's not going to find one solution that's perfect. There isn't one perfect solution, so it's not always going to arrive at the same answer. It's going to arrive at different answers in different ways if you slightly just change the values that it began with differently, and if you introduce different data streams or data sets that it learns from and how to do this encoding and figures out, and it's going to learn different things, what's important and not important in this data stream. And you can't predict that, which means that it's going to be a lot harder than a function that you can predict how it learned or what it figured out. And there's different solutions to what to figure out important. Like maybe it looks at the tip of the nose in one data section. Another one doesn't learn to look at the tip of the nose, but the bottom of the nose. Or it looks at a different part of the face, 10 different data points on the face. And you can't predict that, which makes it a lot harder for a guy on the other end to predict it. But what's even cooler is this data thing. It does something they have something that it could be dynamic and changing. It could be an encryption key that keeps learning new ways of encoding things. These new ways of encoding things could mean that the longer you run it, the better your encryption gets. The fancier and harder to decode it, but because it's always changing so much on the fly, it's not the same function, it's a function that really updates and changes, that it's a lot harder to look at a long stream and figure out what's going on. It would be kind of like looking at the English language, which is something we use to communicate, but you're trying to learn the English language, but you have texts from old English that we can't recognize anymore. And nowadays more on texts, and you only have a little bit of each from each data point, you try and put it together. You're probably not going to learn English because the data is just too very from old language that we can't recognize now from new language. So it'll just be like a language continuously updating and hard to work backwards from a little bit of scattered data points. Also, this will turn the coding encryption into an actual language. Now, the benefits of languages are some of the hardest things to decode because there isn't as much of a pattern. So this is why languages have words in their own grammar system, and this will develop words, its own grammar system and syntax, such as the Navajo code talkers, which they had their own words and language and syntax in every way that you can't just go to Navajo. You have to actually learn the language Navajo. You can't just put it through a cipher where you look at how common certain letters or patterns are because it's so complicated. And I hope you found this interesting. Oh yeah, in this coding stream, we could put on each little individual computer and widely disperse it so all electronics could develop their own languages. So it could be tens of thousands of languages, making it even more complicated to learn. It might even bypass quantum encryption because you're learning a language, and quantum encryption relies still on quantum decryption and quantum code breaking still relies on finding mathematical patterns that languages do not have as much. Well, thank you for listening. I hope you found this interesting. Please like and subscribe. I'm trying to reach 10,000 subscribers in a year, 1,000 subscribers in a year, which is really hard, and 40,000 watch hours, but with your help, I'm sure to do it. If you have any questions or comments, please leave them in the comment section below, or feel free to DM me if you know my contact. Otherwise, I don't want to give it out. And please try to get others to sign up. Thank you very much.